All right, right. So it seems like we're finally live. My name is Simon Arronson, and welcome to this talk titled Attack of the Killer Whales. In this talk, we're going to explore the possibility of running chaos engineering on Docker. Most of you have probably heard of chaos engineering, thinking of tools like Chaos Monkey that required all of these Spinnaker things to be set up in your environment, or using something like Litmus Chaos to do chaos engineering on Kubernetes. But in this talk, we're going to focus on doing this on pure Docker using open source tools. And as I said, my name is Simon Arronson, and I work at K6 as a developer advocate. I quite recently became a Docker captain, which I am truly thankful for. And I'm also the maintainer of the Watchtower repository that many of you might have tried at some point to get your Docker containers automated or the updates automated. If you want to talk to me after this talk, you'll find me on Twitter where I'm 0x12b. So this is not going to be a really deep dive or anything like that. We're going to scratch a bit on the surface. We're going to talk a bit about what chaos engineering is, why it is important, and how we may do it on Docker. We're also going to do some demos just to see how we can get started with it. So what is chaos engineering? It's really fun to think of it as just breaking things for the sake of breaking them. But that's not really what it's about. We don't just want to burn things because it's fun when they burn. I mean, okay, it's a little bit about that as well, but we want to make sure that all the effort we put into making our system stable actually work as we intended them to. And if we have a look at the formal definition taken directly from the principles of chaos engineering, they say that chaos engineering is the discipline of experimenting on a distributed system in order to build confidence in the system's capability to withstand turbulent conditions in production. Or, in less formal talk, uh, trying to break things on purpose in a controlled manner to make sure that they don't break later when we're not in control. And if we listen to Jim Scheibmeyer, who's a principal analyst at Gartner, he says that the reality is that avoiding chaos engineering is somewhat equivalent to embracing crisis engineering. And I really think he hits the nail on the head there. If you systematically and empirically try to expose weaknesses in your systems, or your infrastructure, or your architecture for that matter, you'll obviously be a lot better equipped to deal with them before a real incident even occurs. So, what is it that we try to do? We try to test for the unknown unknowns. And I really want to emphasize this. Unknown unknowns are really hard to prepare for. So, simulating stormy weather conditions using real world circumstances are most likely our best bet for exploring those territories. And if we're already aware of critical weaknesses in our systems, we need to, of course, fix them before we get started with chaos engineering. There is really no point in testing for something that we already know. For instance, if we know that we only have one database instance, then we already know that if that were to fail, then we are totally screwed. And we don't really need to design an experiment that brings the server down to understand that. And as with most DevOps practices, it's always good to start small. So we talk about something that we refer to as minimizing the blast radius. And the point is that until we get the hang of what we're doing, we shouldn't really get anywhere near a production environment with this. While the goal should be to do chaos engineering in production eventually, a staging environment usually has enough similarities to serve as a dojo of sorts where we can practice our craft and sharpen our skills prior to taking on the big boss production. Because causing a real outage and not having any idea on how to get things back to normal or stable, or maybe even how to cancel the experiment that we're currently running, that could have devastating consequences, both to revenue and morale, and depending on where you are and at what company, it could also be really bad for your career at that company. So keep this in mind even as you start to progress towards bigger experiments in production, that we would want to contain the blast of our experiment as much as possible and only try to affect the services that we are currently testing. But as chaos engineering practitioners, we need to also be allowed to do experiments that have short-term negative impact. So it's a little bit of a mix between both. But rather than taking everything down, we want the impact to be as small as it can possibly be while still allowing us to build confidence in our system's reliability. So how do we go about actually performing chaos engineering? We can do it multiple ways, and we're going to do a little bit of a scaled down way in this demo that we're going to do right after this. But the process is about what we see on the screen, more or less. So first, we want to define a steady state, and that is as in, how do our systems behave when things are normal and under normal circumstances? This could be things like number of instances of a replicated service, what CPU and memory usage each container should have, concurrency limits of what to expect in terms of very parallel users, for instance, that access a web page, or whatever else you can think of that will let you know that conditions are actually stable. And once we have that steady state defined, then we want to build a hypothesis. We need to formulate a hypothesis that we may use to determine if our chaos experiment was actually successful or not. Using this hypothesis, we will later be able to draw conclusions from the actual outcome by comparing it to the metrics, for instance, that we gather during our test or our experiment. And the hypotheses that we write should be written in such a way that they build upon the expectation of a positive outcome. A hypothesis that expects the outcome of an experiment to be negative or a failure, that should rather be a prompt to take additional actions prior to doing the experiment. Go ahead and test that our strengthening efforts have worked. So, in short, our hypotheses should be formulated to confirm the reliability of our system rather than proving that it's already broken. As an example, if one of the containers responding to user API requests fail, the performance of our system will not be degraded by more than 10%. That's a much more reasonable hypothesis than, if the container responding to user API requests fail, our system will be unavailable until a new one is in place. We can't really do that much with the second one, so we always try to go for a positive outcome when we write these hypotheses. And once we have our hypotheses down, whether it's on paper or in a system or part of our test that we're automating to run in our CI, then we need to design an actual experiment that simulates the circumstances that our hypothesis describes. And if we use the positive hypothesis example I just read for the previous step, this would mean that we need to inject some kind of failure or chaos into our cluster, causing one of our API containers to either fail or terminate. And while our systems are affected by the failure, we also want to probe them to make sure our hypothesis holds true. For our API example, this would mean exposing the system to traffic similar to what we have in production, and making sure degradation in terms of latency or request failures indeed stays below 10%. For other scenarios or hypotheses, it might make more sense to look for something completely different, like probing for error rates in system logs, measure resource consumption, or check for data corruption. And if our system at any point drifts away from the steady state, then we immediately want to terminate the experiment and let the systems recover, rather than keep pushing them and possibly creating even bigger failures than we were expecting from the get-go. And we want to either let them recover automatically or by performing rollback actions. It depends a little bit on what we're testing. So for instance, if we're testing whether we can introduce data corruption in a database, it might be hard to just let it automatically heal. So we might need to do some rollback there. While at the same time, if we test a container that is just terminating, then we might be fine just waiting for it to start back up. And the point of this whole experiment is that the harder it is for us to make our system drift away from the steady state, the more confident we get about our system's actual reliability. Okay, so now that we've defined the steady state, built an hypothesis, designed an experiment, and measured the outcome, then we, of course, want to fix the issues. And we need to make sure that we actually address any issues we might have identified. And until this is done, it's really no sense of doing any more experiments. So we can do the experiment until this point and start to fix the issues so that we know that we've at least somewhat tried to remedy whatever we found before we try to break it again. Otherwise, we already know that it is broken. And once we believe that we further strengthen the reliability of our system, then we just repeat the process. And we continue to do this over and over and over, hopefully avoiding any on-call incidents that might otherwise have occurred. All right, so that was a bit of an intro to chaos engineering. We have about 15 minutes left, and I'm thinking that we're going to do some kind of demo. Let me just start by switching screen. All right, so we're now in a terminal, and hopefully you'll be able to see what I'm doing. Awesome. Okay, so to be able to show you this from beginning to end, we'll use a tool called Multipass. It's a handy little tool that will allow us to spawn a Ubuntu image or an Ubuntu VM using a CLI one-liner. So what we want to do here is to run Multipass, launch, CPUs, disk 10 gigs. We'll set the memory to 16 gigs and we'll name it Killer Whales. Okay, so somewhere I launch CPUs, disk. My bad. All right, so while we wait for that one to start, what we're going to do here is that we're going to use a tool called Pumba, which is a chaos engineering tool made specifically for Docker to try to simulate a host or a container failure in a load balanced web server pool. And we're going to do this just with regular Docker and Nginx, so nothing fancy here. All right, should be done any second now. Awesome. Okay, so let's drop into a shell in that container. Or that VM rather. Okay, so we're now in a Ubuntu shell. So we'll go ahead and quickly install Docker. And as part of this, it's actually funny that the previous talk was about the Compose 2 API or the Compose 2 release. We're actually going to use Compose 2 as part of this. It will be basically exactly the same as it would with Compose 1 for the sake of this demo, but it's cool to actually be able to show off that it works. And as we have some waiting time here, so if you have any questions, feel free to drop them in the Q&A tab as we wait. And I'll try my best to answer. So I'm gonna talk a little bit about the setup while we do this. So we're first gonna do a test run where we only spin up one Nginx container, just to make sure that we understand what is going on and why. And then we're gonna set up an additional 2 containers and load balance that behind an Nginx, just to see how we could use this to actually remedy or to do any actionable tasks based on what we find during chaos engineering. So, all right, we now have Docker installed. So let's also go ahead and add ourselves to the Docker group so we don't have to write sudo. Demo gods are not with me today, but hopefully we'll manage. All right, so now we have access to Docker. Awesome. And now we also want to fetch Pumba. So Pumba is a CLI tool, and you can use it to directly interact with your Docker cluster or your Docker node. So we'll just make it executable and move it over to bid. So we have it in our path. Okay, so then we have Pumba. Awesome. Now we'll go ahead and install Docker Compose v2 as well. Excellent. Now create the compose file for our first experiment. I'm going to name the node web node. I'm also going to set that as the container name. We're going to use a Nginx demo image that will reply with some data upon being called. Let's map that to 8080. Okay, looks about right. Now let's try to spin these up. Now, just to be able to show you what's happening, we're going to start a tmux session. Let's do it horizontally. I think that would be easier to see. Okay. So if we now curl the endpoint that we just mapped, you can see that it responds with the server address, the server name, what URI we called, and some timings that I added just to make sure that we know how fast or how performant it is. And if we run this a couple of times, we can see that it stays around the same time. Awesome. Now let's introduce Pumba to this. And in this case, we're going to use net emulation to introduce some latency to the response of our request. So we're going to use Pumba net emulation or netem. And we're going to say that we want the TC image for this to be IP route 2. And we'll set the duration to 10 seconds. What we're going to do is delay, as I said, and we're going to do a delay of 3000 milliseconds. And we want this to affect the web node. So as we saw previously, the web node takes about 0.017 seconds to execute. Now if we run Pumba and do the same thing again. Did I not press run? Okay. Now we can see that we actually have a delay here, that we're waiting for something. And that our response was response time was a lot longer than it was previously. And then it's back to normal. Now, what would happen if we did the same thing, but instead did it with a pause than a delay? Let's see. Okay, so running that, jumping back and doing a request. And we can see that it will just continue to wait on either until it times out or until the pause duration has passed. And this actually gives us some pretty cool actionable insights. We obviously need some kind of redundancy here, right? So if this were production, we would have a single point of failure here, where if the server for some reason stopped responding, then we wouldn't be able to serve our users. So let's go back into our compose file. We need to do some changes. All right, so we currently have one web node. We obviously need more, so let's add 2 more. Also remove the port mapping from the web nodes. Okay, so we have web node 1. Let's just go ahead and copy that. All right, so now we have web node 2 and 3 as well. Great. And we also need our load balancer, and we'll use Nginx for load balancing. See that I'm unfortunately starting to run out of time. Hopefully we'll be able to finish before we're booted from the stage, but let's see how it goes. Okay, so now we instead use the load balancer as our ingress, and we're going to set that up to forward to the other 3 nodes. So let's also create an nginx config file. Here we'll set it up with 3 upstreams. Or 3 servers as part of our upstream, rather. All right, and we're going to create a server as well. For the location, any location that starts with a / we want to proxy this forward to our load balancer upstream, together with any arguments that we provide. We want to distribute the connections using a least amount of connections detection algorithm, and we want to add a timeout as well. So if we, for some reason, are unable to reach our servers, then we'll just skip ahead to the next after that timeout. All right, so that is it. Now let's see if we can get this up and running. Oh, okay, sorry, my bad. There we go. Also, of course, need to kill our previous node. All right. So now if we go ahead and curl the same URL, something is obviously wrong in my nginx config. And I don't think we'll have the time to troubleshoot that, unfortunately. I'll make sure to add a repo for this, so you can go ahead and try this out yourself. But the end result that we wanted to actually happen from here was that the load balancer would split out these request across these 3 nodes. And when we stopped one of the nodes or paused it for a duration of 10 seconds, for instance, then it would automatically jump over to the next server, and we'd be able to get continuous access to our web services, even though one of the nodes failed as part of our experiment. All right, so I'm really sorry that I wasn't able to show you that, but demo gods, unfortunately, that happens. But we have a question from Kevin Duane, and he asks whether the code/.scratch environment is a special dev setup. And no, that it's not that. It's just a folder that I use to store my code space, code source repos in. So nothing special about it. All right. Once again, I'm really sorry that I couldn't show you how it actually worked. Oh wait, I actually might be able to do that, to be totally honest. Yes, I just spotted the error. Okay, so quickly now. Okay, so we won't be able to do that. Thank you so much for listening, and hope this was at least exciting to watch. And hope to see you soon again, and maybe talk a little bit more about this then.
Thank you, Simon. This was great. Really fantastic. Great to see so many people watching. Thanks again, Simon.
Thanks.